mean, I crashed about half an hour ago for processes for today, but I learned.
Okay, so let's get done.
Yeah. No. I don't think. Yeah. I think the graph. You can also. It says that you can also count the as we did in class.
Why I registered for my work?
Yeah. Yeah.
Oh, okay. Okay. All right. Welcome to class, everyone. So today, what we are going to do is we're first going to talk about algorithm correctness, and then we're going to go over project 3 a little bit. So we're past the late deadline, so now you can't turn it in anymore. So I can show you my solution, and then as a sort of practice for the quiz and just making sure that we really understand linked lists and arrays, using arrays as data structures and big O notation, we're going to think about the runtimes for all 8 of those methods that we wrote for project 3. So yeah, let's go into today. So what we've been doing for the last week or so is talking about the runtimes of algorithms, right? Given an input size n, what function should we use to model the runtime of some algorithm? And so that's things like constant time, big O of 1, quadratic time, big O of n squared, etc. But we haven't really been talking about how do we, and we formalize that, that's kind of the big O stuff, is talking about that formally, but we haven't talked about formally what do we mean, how do we know if an algorithm is correct, meaning, and what does that even mean? So we're going to say that an algorithm is correct if it returns the correct value for every allowable input. So our example today that we'll start with is an algorithm to compute the maximum value in an array of, say, doubles. And so any algorithm that takes in an array of doubles and returns the value that is the largest one, we would say, for all possible inputs, we would say that's correct. So how do we prove that something is correct? Well, let's start with the easy case. What if an algorithm is not correct, right? So maybe I'll make this just as, okay, that's bigger, making it smaller. Okay, so what if we have an incorrect algorithm? So I will just give you a minute to look at this and think about whether this algorithm is correct. And I guess, kind of spoiler alert, it's not. But I guess if you're looking at this page, you already can see an example. But if anybody has any ideas for examples of inputs that this would not be correct for, or what is the general class of inputs that this algorithm would not be correct for? And it's the right idea, it just has a mistake in it. So this would be kind of probably if we had the right idea for finding the max value in an array, but we just have a small bug in our program.
So you have an array of doubles,
Mm-hmm.
and it's going to compare the double to an integer every time. So isn't that going to cause issues because current max at one point is going to be equal to an integer?
Well, where?
We know I represents a place in the double.
Yeah, exactly, yeah. But yeah, no, good thought. Yeah. What was that? Well, yes, close. So we only have to start at 1 because our current max is the very first one at 0. And so we don't, if we don't have to compare to that. Yeah.
So it's not going to check the last value in the array given because x dot length is subtracted by 1, and so when it's equal to the sort of last index of the array, which is x dot length minus 1, it's not going to test that.
Yeah, so if our max is the very last one, then we would miss that because we're only going up to index, this is a strictly less than, so we're going to only check the index x.length minus 2 is going to be the last one we check. So, we can say, okay, this is not going to work for anything that has its max is the last index. And so we can just give a counterexample. So we know that, but to say that this is incorrect, we really only need one example of it being incorrect to say the algorithm's incorrect. And so that's what a counterexample is. It's just one instance that, one input that our algorithm would not be correct for. And so the one I happen to put here has 100 in the last spot, 10 in the first spot, but yeah, anything that had its largest value in the last spot. This is kind of not that great an example because it's just this kind of little error that we made. It's not that the idea behind walking over the array to find the max is wrong in any way, but it is an incorrect algorithm. Is this making sense? Yeah.
So to make it correct, you just change it to I is less than or equal to x dot length minus 1?
Yeah, either less than or equal to, or just remove this minus 1 and keep it less than. Right. Either of those, yeah. Okay, so perfect. Okay, so if instead of this code here, we had, I think I even have this in Eclipse because I was worried about making some sort of syntax error, so I think I have this. Oh yeah, okay. So I have this right here. So let's say we fix this. Let's say we remove this. So now the question is, how do we argue that this algorithm is correct? Anyone have any thoughts? Yeah.
Pass in a range of different double arrays, see if it works. If it works every time, we're good to go.
Yeah, so we could generate a bunch of, we could pass in a bunch of inputs where we know what the output should be and have our program, check that they're correct. But realistically, I can't generate every single double array, right? And so we want something that is going to not require us to do that, something that can just be a general method. And so what basically the computer science community has really embraced since this was invented in the 1960s is a loop invariant. And so you're going to go more into this in 246, I think, because it's kind of feels a lot like mathematical induction, if you've seen that before. In this class, what do you really need to understand? You need to understand what is the definition of an algorithm being correct. So make sure you understand this. And then also just understand if we want to formally prove that an algorithm is correct, one method is a loop invariant. But I will try to explain this a bit. So if we think about let's think about our array max. We actually can, we can definitely give some intuitive reasons why this is correct. I mean, it's super simple, but if someone asked you to sort of prove why this was correct, I bet that you could give some arguments, right? So, yeah, I mean, if you had to argue why this was correct, does anybody have any ideas about what kind of argument, like what's an idea for that? Yeah.
Could you just use straight up mathematical induction, like on paper?
Yeah, I guess it's true. Yeah, so, well, what were you think? Like
you prove that it works for like the smallest case possible, so it's 0.
Yeah.
Which it does, because you just say it start at 0, and then the max is 0, and then congrats, the max is 0, you know? And then
Yeah.
and then you'd use it, you'd compare, like you'd make a general rule, substituting in k for for x, and then you compare that to k minus 1 for x. And then you
Yeah.
see if you could get the left-hand side equal to the right-hand side using k and k minus 1.
Yeah, but I mean, so I think I got a little lost on your implementation, but the idea of mathematical induction, I would think what that would look like here would be, okay, consider the case where we just have a 1-element array. Well, I should return that single element. It's definitely the max. So now I have to somehow think about how do I go from given that my algorithm works for a length k array, I have to prove that it works for length k plus 1 array, or something like that. But, yeah, which maybe that would work. But, okay, even thinking, not even thinking of the method, just this what we've written in the code. If you had a friend who doesn't know Java at all, and for whatever reason they were explain how this works, what would you tell them? Yeah.
It's stratify each segment of the code, basically separate it based on where the semicolons are, go over what each one of those steps mean, and then prove that hey, it goes over every value, it does compare every value, so it's a machine, but basically break it down to each individual step, and then show that each step does exactly what you expect it to.
Yeah. So, and the sort of nugget of insight here for this particular algorithm is that we compare to every single element of the array, and if it's bigger, that's the one that we keep, right? And so I think that that is basically the intuition that we want to be able to capture with loop invariance, is we want to be able to capture the fact that, in this case, we're going to look at every single one. And so, yeah, maybe let's do this example. Honestly, I think that the example that I took from the book is not very good. So we're going to see if we can do some on-our-feet copy-pasting, because this is way better. Okay, it'd be so nice if my paste. Dang it, didn't happen. That's okay. Okay. So yeah, we're gonna do this one because I think it's a much better example than the book's example. So let's look back at the sort of formal idea of loop invariance. So the idea of loop invariance is that, so we want to say our overall claim is that this algorithm is correct. So let's go back to it. Our overall claim is that array max always returns the max value from x, right? Does that sound reasonable for what we want to prove here? Okay, so what is in order to prove that, we're going to have a subclaim. And that subclaim is these, I guess we have a series of subclaims, but these iterative script L's. And basically, we want this claim, we want it to be easy to go from if the claim is correct at LK, then our algorithm works. So that's the big idea here, is that we make these subclaims, and at the last one, it should imply that our overall claim is correct. So we'll call this the overall claim, and our last subclaim should imply that our overall claim is correct. And so to give the flavor here, our subclaims for this algorithm are going to be that as we step over the, it's going to be that cur max is the largest value from x from 0 to, if we're currently at index j, or we'll say, we can even use the same indexes in our algorithm, or in our implementation. So our subclaims are that this value, cur max, is the largest value from this subset of the array, right? And so can anybody tell me why, if we get to the end, so let's say when I equals n, so this is our subclaim. If subclaim is true when I equals n, why does that imply that our algorithm is correct? So cur max, it's changing every time, or it might be changing every time. So it could be changing, our first, let's say our input is, let's say the input was 1, 2, 3, 4, 5. So the first time I go through cur max is 2 at the end of the for loop. The second time I go through, it's 3, etc. And so if this subclaim is correct, then how do we argue that my overall claim that the algorithm is correct is implied by that? Yeah?
Because n is the largest, the largest that the claim can be.
Yeah, we've made it to the end. It's exactly what we wanted our algorithm to do. We wanted our algorithm to give the largest value in the whole array, and now if our subclaim is true when I equals n, then that means that we're at the very end of the array, and it's the largest value. Cur max is currently the largest value in the array, so the algorithm is correct. Yeah, so formally, what these subclaims look like, so let's come over to the writing. I want to get rid of this. Delete. Erase. Okay. So let's look at this. So, okay, so our subclaims are that cur max is max value for our input array x from 0 to up to our current I. And so what we want to do, and then this is where it kind of feels like induction, is we want to say, is this true for, we have to check, is it true for I equals 0? Well, oftentimes, and in this case it's especially important that we know that this is x from 0 to 0. So this is like empty. This is an empty array. And so we often say in math, when we're talking about is something true about the empty set, it's always true. So we say that it's vacuously true. So this would be vacuously true. And then now we say, assuming true for I equals k, I need to show that it's true for I equals k plus 1. So yeah, this is our induction coming in. And basically, this is super simple. If I'm somewhere in my array, it's like minus 10, minus 11, 5. I'm at this spot, and we got some more stuff. I'm right here, and I guarantee to you that cur max is the biggest up to here. So I already gave you that fact. Now you just need to look at this code and say, if that is true, and I increment 1 more, I go to k plus 1, what does the code do? When I is k plus 1, well, it just executes this if statement, right? Like, does what's in here. And so now I look at this, and I do my if, and now we can just say, well, okay, yeah, if cur max was the biggest, okay, here we are. So now we've got k plus 1 is I is k plus 1. So yeah, we do what's in here. We do this if statement. And either it's bigger than the current cur max or it's not. But either way, after we go through that code, cur max is going to be the biggest up to in x up to k plus 1, from 0 to k plus 1, right? Does that make sense? It's just very, very simple, and it feels kind of, in a way, it can kind of feel silly because we're really just writing down that intuition that we had that, yeah, if you walk through over the whole array and you check, is it bigger than this cur max? If it is, or if that slot is bigger than cur max, then update cur max. But this is how we formalize that correctness. And yeah, so now that we have this base case, now that we have the base case and we have the inductive step, essentially, we've proved that this is going to work up to the end. So now, when I equals n, cur max is max of x, starting at the beginning all the way to the end. And that's exactly what we wanted. So our subclaims imply that our algorithm is correct. Again, just so that you don't worry, I'm not going to ask you to go through something like this, but may ask, what does it mean for an algorithm to be correct? Yeah.
So this is a really long time and a really complex algorithm. Are there more efficient ways of checking?
So one thing is, this is really only for loops. So not all algorithms even have loops in them, for example. And also, a lot of times, we only actually make these proofs when there's kind of a question about whether it's going to be correct. Or for the more, kind of tricky or confusing parts of algorithms. So you probably wouldn't, except as an exercise in class, just to get used to the procedure, you wouldn't do this for an algorithm like for this part, for even like a subpart of an algorithm that was like this. Like, this is pretty clear that it's correct. But another, I think it's often, being rigorous like this certainly can help you catch errors. And yeah, I guess the main thing is you're not going to do this for every part of an algorithm. It's only going to be for the kind of hard ones. And so, yeah, you're not going to do these trivial proofs for like every single for loop in an algorithm. Cool. So, great. That is our discussion of algorithm correctness and loop invariance. And so now I want to move on to project 3 and also its runtimes. So I think actually those of you so regarding project 3, I know those of you I think in Assad's lab may not have gotten your grades yet because he was super busy this week, but you should get those today. And then also, if you're in if Emmett is your TA that grades your work, you may have gotten points off if you divided by 100,000, even though it's what I told you to do. So he's going to go back and fix those. So hopefully that resolves any grading questions. Are there any other grading questions on project 3 that anybody wants to ask, or like logistics questions or anything like that? Cool. Great. So yeah, let's look at project 3. So a few things that seemed like were confusing or possible that you may have gotten, may have done in like, I think, a more complicated way than you needed to. So I'm going to go down to the timing portion. So in my mind, the simplest way to do the timing was to first just to create one single array of random integers. So for example, I called this array ARR. Okay, so this array just holds a bunch of random integers, and I only need to make it once, right? And you'll notice that I'm not timing making the random integers, because that's going to throw off my timing for my methods, right? If I time how much time it takes to make these random integers, then I'm including that rather than just timing the time that it takes to add those into my array, for example. So any questions on that? Cool. So just made that one array to hold random integers, and then basically for each method, we just want to, so my method, if I'm timing add first, oh, it looks like I actually did not even do this right here. That should be array at I, right? So if I want to time adding first, then I'm going to walk over the indices from 0 to, I guess num is 5,000, so 0 to 499, and I'm going to call add first that many times, and then I have start time, and I subtract start time from the time at the end, and that gives me my time at the end. So just a simple, you could have put this in a for loop or like in a loop or in a function or a method so that you weren't writing it a bunch of times, but what I'm pointing out here is just having the time start and end just around calling the method and not including any other code in there. Cool. Yeah. So now if we go on to the implementations, so for the array data structure, the idea here was to have a internal array. I called it A, but this internal array, and so this internal array is just going to have some initial capacity. And so for this project, it would make sense that when you construct it, you would have that initial capacity be 5,000 because you're going to add 5,000 in. But you could have made it like 10,000 if that makes you feel more comfortable. But what you didn't want to do is have your internal array change size every time you add something in. So here you can see that the add last method, there's already, like, we can just put, when I take in a new integer, I can just put in that new integer at num entries is how many I currently have in my array. I can just put that in at the index num entries, right? And then I need to increment num entries. Are there any questions on that? This idea of having one internal array that you initialize to some large capacity. You know you're not going to put in anything more, so you're good there. Okay, awesome. Also, I think people even doing this correctly, but still, here is an add first method, and you'll notice that we don't have to create a new array or anything, right? We just have this internal array. All we're doing is, okay, we increment num entries. I guess that probably should be at the end instead of first, but I happen to do it first. And then in this while loop, we start at the back of our data and we move everybody over one at a time. And then we can put in our new int at slot 0, right? Cool. Yeah, get n, just one line, right? Really easy. And then toString, walking over the whole thing. Yeah. So any questions about the array DS implementation before I go to the linked list? Awesome. Okay, and then linked lists. I think we did a lot with these, and you had a lot of code available. So I wasn't hearing from people that were struggling with this one as much. So unless anybody, we're actually going to look at these closely when we do the runtimes. So unless anybody wants me to specifically look at one of the 4 methods, I will move on to the runtimes. Okay, so let's move on to our last fun part of class where we are going to, where are we? I don't have it open. It would be really nice if I could find this. What? Oh, yes, okay, here we go. Okay, so here we have a table, and we have ArrayDS and linked list DS, and we're just going to write down the big O runtime of each of these methods. And so we're going to do one together first, and then after that, we're actually going to stand up, and we're going to have everybody go to the side of the room. One side's going to be one runtime, one side's going to be another runtime. You're going to have to go to the side of the room that you think, of course, that you think is right for each one. It's going to be really, really fun. But let's do one together. So how about add first for array DS? Okay, that is an ellipse. So we're looking at add first from array ds. Okay, so here we got our code up here. Any thoughts on how can we think about what the runtime of this method is? Yeah.
Check if there's any loops.
Yeah, that's a great idea. So why would a loop be a good thing to look at?
Each time you get a loop, you touch every element usually, so you have n squared based on the loop.
Yeah, pretty much if I am basically looping over an array or a linked list, even if I'm not touching every single one, even if I'm touching every other one or not the last one, then that is linear. So that is big O of n. And so for add first, really the thing to really look at here is this while loop. And then also when we think about how did we sort of draw a picture of this? Well, in our picture, we had to draw like, okay, this one's going to move there, this one's going to move here, this one's going to move here, this one's going to move here. And so I'm basically doing n things. If I have n items in my array, then I'm basically doing n things. Okay, so we would say that this is big O of n because it's linear. It has to walk over the whole array. Okay, so yeah, now you can take a minute to like secure your things. What we're gonna do is, so let's see. This side is gonna be big O of 1, and that side is gonna be big O of n. And we are just going to use our bodies to show which runtime we think each one is. Okay, so n is this side, 1 is that side. Okay, so let's go back. So let's think about add first for linked list ds. So I'll put the code up. Okay, this is add first for linked list ds. So do you think that is n or constant? So this was add first, and okay, we got a vote for constant time, but who knows where else? Okay, we're putting it back.
Oh, come on, Chris. Come on, man. Yeah, stand up.
Okay, I'm not seeing any votes for constant time, or I'm not getting any votes for, for linear time. So great. And anybody want to tell me why do we think that this is, why is this constant time? Yeah.
When you're adding first for linked list, you're just putting it in one slide and have to push everything out.
Yeah, I'm just reassigning head. That's all I'm doing. So that's constant time. Awesome. Now let's look at add last for both of them. So let's say array ds add last. Okay, here's our code for array ds add last. How about, do we need to move? Nope, exactly. We're just assigning to an array and we're incrementing. Awesome. So I'll just put this in without scrolling over. We'll look at it in a second. Okay, how about add last for our linked list? Here's our code for that. This one's a little longer, the code's longer, but someone else want to justify why you're staying where you are? Yeah, well, okay, let's see. How about in the front here?
Okay, you're still changing a set amount of pointers.
Yeah, I'm just, I might have to change a couple things, increment. I've been making a new node, but we're assuming that that's constant time because we're just setting some fields. And so, this is constant time. So add last for both is constant. All right, so now we're going to look at get n. So first, let's look at array ds. Okay, this one Hopefully not too hard. Won't even make you do anything. Clearly, we're accessing something in an array and we're returning it. Like, we can even say that is precisely 2 operations. So that is definitely constant. But let's look at linked list. We're looking at get n. So, okay. Here we got get n for linked list. Where should we go? It's going to be so fun. We're having so much fun. Don't tell me you're not having fun right now. Okay, somebody who hasn't said anything today, have any ideas? Yeah, why?
We have to cycle through the whole linked list.
Yeah, we gotta cycle through the whole linked list. Maybe sometimes it's at the front, but in general, in our worst case, it could be at the end or it could be in the middle. And so that's why we are big O of n. Okay, finally, we got toString. Let's go to our array toString. Okay, anybody want to move? Not seeing anyone? Okay, great. Again, we got a for loop, right? We got to walk over the whole thing to print it out. So it's O of n. And then similarly in our linked list, we happen to be using a string builder here, but doesn't change anything. We still have to walk all the way over to the end. And so this is O of n. Okay, so yes, thank you for participating in my activity. I will put this on the today's page. But yeah, I think it's on the practice quiz. These kind of questions will be on the quiz. And so yeah, make sure that this makes sense. And if anybody has any questions, you can come up, but we'll end class.
Are you teaching the discrete structures class next semester?
Yeah.
Gotcha. And that's like more the math behind some